All right, let's do this. Get going. This is our last lecture on kinematics. Okay, and in fact, we might get to the geometry of motion. Remember, to this point, you've noticed, maybe you haven't, there's no forces yet. We haven't talked about forces or free body diagrams or anything yet, and that's where we're headed. Probably by the end of the day, we'll definitely be in that range. Okay, I honestly think once we get to this, it gets easier because it's a very structured way of solving these things after we get to the next section. This one is, as you probably felt a little bit, it's like, oh, well, which method do I use? And there's sometimes shortcuts and sometimes not shortcuts, and there's integrals, right? Nobody likes integrals, but we're gonna quickly move away from that as we go along. I wanna do this. Yeah, we gotta do it, right? I'm still in awe that your name was drawn, and you lost a homework, and then your name was drawn, and you got it back. I didn't think that would ever happen, and yeah, you should. You should. Or this is not a very good program, right? Yeah. Let's see. Elias? Is it Elias? Elias? Which one do you go? Elias? You know it's pronounced Elias sometimes.
I'm from New Mexico, I know.
What's that?
I'm from New Mexico. That's the normal version.
Elias's or Elias's? Yeah. All right. Welcome. Mark? No Mark? I got him. Right? It's kind of a weird emotion that you guys go through, right? Like, you want your name to be drawn so you don't lose something, but if you're not here, I don't know, I got to work it out. I still want to get, maybe stickers. I got to do stickers for you. Martin. Welcome, Martin. How do you say that last name, Martin? How do you say that? Excuse me? Oh, interesting. Are you German? Are you German? Like really German? Okay, all right. All right. Welcome. Okay. All right, so what did we just do? What are we working on? Just to refamiliarize yourself with it. We were doing polar coordinates. We derived this stuff for polar coordinates, and we get down to it. And we derived this equation, right? The acceleration, right? Velocity is just going to be r dot in the ER direction and r omega in the E theta direction. So we have a velocity associated with the radius changing. That's on the left. We have a velocity associated with the fact that it's rotating, and that's the r omega on the right there. So this is associated with the r changing. This is the velocity associated with it rotating. Okay, and we came down to accelerations, and this thing blew up on us, right? And so we had the radial acceleration. This is the acceleration outwards of your radius changing. That's what that one is, the radial acceleration. This is the centripetal acceleration. You have to be accelerating back towards the middle. If you don't, you fly off on a tangent, which we witnessed in those videos at the merry-go-rounds. If you don't apply a force to accelerate back towards the middle, you fly off on a tangent. Our alpha is the tangential component. If we have this acceleration, if our omega is getting faster, we should have an acceleration associated with that, and that's at r alpha. And then this right here is the Coriolis effect. I have a zero, just how I always like to picture this, I have a zero velocity in the E theta direction when I'm right here at the middle, but if I take a step out, I have to speed up to that r omega at that location because my radius got bigger, and so I have to have some acceleration. But if I stay put, I don't feel that acceleration. That's why this is a function of my velocity. It has to be moving. Take another step out, I have to speed up, and so on. So that's what that r dot term is, okay? And so the hardest part about dealing with these problems is just figuring out what component is what, right? We did a super simple example. We talked about transforming it into Cartesian coordinates. We're going to do an example today where we have to do that. And then we had cylindrical coordinates. We just add in a z component. All right. And so then we did this really super simple example, and then we started this one, and then I decided not to do it and wait for today. Okay, so there's a little slot. That's what we're gonna take off today. This little slot has this little puck in it, and that thing can move out in that little puck, okay? And so this thing is rotating around, according to the problem statement right here, a constant omega or constant theta dot, same thing. Okay, it starts from rest at the center, and then it asks us for the magnitude and the velocity, magnitude of the velocity and the acceleration at t equals 1 second. Okay, and so when I start these problems, a lot of times I like to do is I just like to write out what the equations are that all my terms are in. So I'm after this velocity equation, or the velocity. Right, and then I'm going to need to get the magnitude of that. That's just going to be r dot in the ER direction plus r omega in the E theta direction. Thinking of things that we know, right? I know what r dot is, right there. It tells me what r dot is, so that part I know. R, I do not know. It doesn't tell me anything about the radius. I just know that at 1 second, right, I'm going to have to know what the radius is at 1 second, but they don't tell us that. So we have a little bit of work to do to find what that r is. This omega, I do know what it is. That was told to us. So all these terms I know except for that r. So at some point, I'm going to have to figure out what that r is. Acceleration, let's just write down that and see what we know and what we have to find. Okay, it's a whole term, r double dot minus r omega squared. The centripetal acceleration in the ER direction plus r alpha plus 2r dot omega in the E theta direction. Okay. Again, just look to know what we have. R double dot, I don't have it, but I can get it pretty quick. R again, I don't know what that is. Omega, I know what it is. Alpha, I know what that is. That's 0. R dot, I know what that is. Omega, I know what that is. So really what I'm after, I need that R right there. Okay. And I need R double dot. Okay. And so what I do, let's start working out some of those terms, right? They tell us what r dot is, right? That's 4t. R double dot, I just take the derivative of that. It's the time derivative of that. So now I know what r double dot is. That was pretty quick, right? Theta dot, that's the same as omega. That's equal to 6 radians per second. And then since that's constant, then my alpha is equal to 0. Theta dot 0. If we take theta double dot, right, the derivative of 6 is just 0. Okay, so now I need r. Like I said before, the last thing I'm missing here is r at t equals 1 second. Right, so I have to go to this. R dot is equal to 4t, which is equal to dr dt. I put all my t's on one side, right? 4t dt is equal to dv. I integrate and I integrate. And this is going from 0 to 1 second, right? That problem statement says what is the radius at 1 second. So my time there is going to go from 0 to 1 second. And this is going 0. Hold on, what did I do? This is ds dt. Ooh, I wasn't done yet. I wasn't done yet. I was going to say what's wrong with this. It was dr dt. Yeah, okay. And that's dv. This is where I messed up. This is dr. Not dv. Everybody get that? Instead of dv there, that should be dr. And then that's what I'm after right there, is that r. Right? So you just carry out that integral. It's a definite integral. And I get r is equal to 2 meters. Right, so now I know what that radius is. Just do a little bit of integration to get what that radius is. Now I have all the components. So now we just go back to that original equation and plug everything in. Or the original equations, that is. Velocity is equal to r dot in the ER direction plus r omega in the E theta direction. So this r dot is just 4t, so 4, and we're doing it at 1 second, so 4 times 1 second, that's 4t in the ER direction. Plus r, we just determined to be 2. Omega was given to be 6. And that's in the E theta direction. And here's my answer for my velocity. It's 4 in the ER direction plus 12 in the E theta direction. Okay. And actually it asked for the magnitude of that. I did not calculate the magnitude of that, but then you just do, if you want the magnitude, you do the square root of the sum of the squares of those two terms, right? And that would tell you what the magnitude is. Okay? Now we just go to the velocity, or to the acceleration now. The acceleration equation. Again, just write it all down. R double dot minus R omega squared in the ER direction plus R alpha plus 2R dot omega in the E theta direction. Plug in all the terms that we have. R double dot we determined to be 4 minus R was 2, omega was 6 in the ER direction plus R alpha was 0 plus 2 R dot would be 4 times 1, and then omega is 6 in the E theta direction. Okay. Plug that sucker in your calculator, and you get for your acceleration vector negative 68 in the ER direction plus 48 in the E theta direction. Okay. Hopefully you see, right, the benefit of using this polar coordinates, right? Trying to keep track of this stuff in terms of I's and J's would be a huge pain in the butt, right? But doing it this way makes it a lot easier. Any questions about this one? Yeah.
Why did you put in a 1 between the 4 and the 6?
Oh, yeah, because right here. Yep, because this is, good question. I said it kind of passing, right? This is 2R dot omega. R dot is 4T. And we're figuring this stuff at 1 second. Yep. I did that on the fly. I knew that was going to be confusing, but I did it anyway.
It was like,
Yeah.
there's now 4 sets instead of 3 sets.
Yep. I did it right here too.
That makes sense.
Yep. I did it up there too. I knew it was going to be confusing, but I did it anyway. Because I'm in charge. Okay. All right. Everybody good? We good? Good. All right. Let's do the next one. What did I do? Oh, yeah, this one. Yeah, okay. Relative motion. New topic. Last topic in terms of kinematics. Then we're going to go into F equals ma stuff. Okay. So this has to do with, make sure you understand this stuff. We use this a lot in rigid body stuff, right? From here on out through the rest of the semester, we do this relative motion quite a bit. It's a pretty easy concept, but it's worth spending a little bit of time talking about it, okay? So this has to do, back to this example of, being on an airplane playing Frisbee with someone, right? And we start talking about, well, how fast is that Frisbee going, right? It depends on what we're talking. How fast is it going relative to what, right? It has to be relative to something, right? And so sometimes that we're going to be talking about the velocity of that relative to the plane. Sometimes we're going to talk about it relative to the Earth or relative to the sun or something like that. You have to talk about speeds and velocities and accelerations relative to something, okay? And there's a way that I can determine how fast this Frisbee is going dependent upon how fast this Frisbee is going relative to the plane and how fast it's going relative to the Earth. And we could come up with an equation that helps us with that, okay? And so we start out just talking about positions, right? And this is probably a review on vector math. If I wanted vector A, if I wanted to figure out where A was at over here, this is RA hat, or RA, bar rather, and I have the position RB as well. The vector pointed to B. There's also a vector that goes in between, right here. That is, we're going to call RA as seen from B. Right? That's how I'm going to pronounce this when I have this slash here. I'm going to say RA as seen from B. Okay, or you can think of that as RA relative to B, right? However you want to think about it. I always just say RA is seen from B. If I was at B looking at A, this is what this vector would be, okay? If I wanted this position A, I could just define that And you remember this is some back or some review for vector math. That if I want to get to A, I can go through B. I could just say, well, A is just going to be RB plus RA is seen from B. Remember that from the math class that you can add vectors like that. RB to RA is just going to be RB plus RA is seen from B. And that's all. That's it right there. That is what we're after right there. That the position of A can be the position of B plus RA is seen from B. The position of RA is seen from B. Okay? And then let's just kind of define these terms. Right? These are positions of A and B relative to origin. That's what these two terms are. And this is position of A as seen from B. That's how I like to say, or you could say relative to B. Okay. And if we can define position that same way, we can also define velocity the exact same way. And we're just going to jump right to that. Right? If it works, right, that positions, I can get to one position. Our velocities are also vectors, and I could use the same arguments how I can get to the velocity of A by going through the velocity of B. Right? Same thing with accelerations. Acceleration to A is just going to be the acceleration to B plus the acceleration to A as seen from B. Okay, and so if we're in terms of like how fast is this frisbee going, just to close out that analogy right there, we could say that the velocity of the frisbee I don't know how to spell frisbee. Is that close enough? Velocity of the frisbee is equal to the velocity of the plane plus velocity of frisbee as seen from the plane. And so that kind of nice little analogy to think about. If I wanted to see the total velocity of that frisbee on there, it's going to be the velocity of the plane plus the velocity of the frisbee as seen from the plane, right? How fast is it going relative to the plane? And we add on to it how fast the plane is going. Well, that's going to be the total velocity of that, right? And you can keep going with it. You can keep going and say, oh, well, how fast is the surface of the earth moving? And then how fast is the center of the earth moving? And then how fast is the sun moving? And you can keep going like that with the same arguments that are here. So this is it. The old book, I just want to mention, you're doing 13.164. The back of the book had the wrong answer. The old one, 5th edition. We're now on the 6th edition. I don't know. Do they have the answers in the back of the book of the 6th edition? Anybody looked for that?
Yes.
What's that?
For the even questions.
For the even questions. Okay. So just this is the right answer. I think at least in the 5th edition, they had a negative in front of that 200i, and it was really throwing people off. And so I just wanted to point that out. So if you're doing your homework, this is the correct answer right there. This is, even though it says wrong answer, it really means there is the wrong answer. Here is the right answer. Positive there, negative in the J. Okay. All right. Let's do an example. All right. An airplane is pointed due north with an airspeed of 560 miles per hour. This is the airspeed. So I think airplanes, somebody told me once that it was a pilot, the airplanes can have like this little sensor on it that can measure how fast the air is traveling through. Is there any pilots in here?
Pitot tubes.
What's that?
Pitot tubes.
Pitot tubes?
Pitot tubes.
PO tubes.
Yeah, they like have the measure the air as it comes in.
Okay. Yeah, then it comes out the other side. Boats have the same thing, the velocity of boats and stuff, right? They have a little thing that can sense the water going through it. Anyways, so it's going 560 miles per hour relative to the air, because that's what it's doing. It's sensing the air as it goes. And then the wind is 60 miles per hour at 30 degrees as shown. I haven't shown it yet. Let me show it here. The wind is doing, well, that's not. It's got like a thing here. This is 30 degrees, like that. Okay. As shown, right? And then my airplane's over here. is traveling in it. It's beautiful, beautiful airplane, right? It's pointed due north, right? And it's traveling at 560, okay? And then what it's after, what it asks us for is the ground speed and course. So like how fast is it going relative to the ground? And then the course has to do how far off of north are you traveling? Or is your angle, I guess, right? So this is velocities, just asking us about velocities, right? So we say we're gonna use this, right? Velocity of A is equal to, this is what we had on the previous page, velocity of B plus the velocity of A is seen from B, right? Put it in terms of our variables here, right? I want the velocity of the plane. That's what I'm after, the total velocity of the plane. And that's going to be equal to the velocity of the wind plus the velocity of the plane as seen from the wind. Let's put it in terms of our variables. Okay. So some of these terms, right? The velocity of the wind, that's the first thing we might want, right? Velocity of the wind, we're going to put that in vector notation. Right, so they said the wind is at 60 miles per hour at 30 degrees. And so I'm going to break this thing into the X and Y components. My coordinates over there, X and Y components. So I could look at this component here. That's going to be in the X. And that component there is going to be in the Y. So then my V wind is going to be 60 times cosine 30 in the I plus sine 30 in the J. That's all I have to do. I just need to take that and I break it into its I and J components. Right? And then the other part of it, the V plane as seen from the wind, that component, that's just going to be 560 in the J direction. Right? Because again, that's how it's tracking. It's 560 in the J direction. It's pointed due north, right? Pointed due north, and then how fast it's going relative to the wind because of the pinometer. What would you say the one thing was? PO tubes, right? Not the pinometer, but the PO tubes, right, are telling us that we're going 560. So those are all the components. So you just add the two together now, right? Everything's in the I's and the J's. You just keep the I's together and the J's together. So my V plane is equal to, right, 60 times cosine 30 in the I plus sine 30 in the J plus 560 in the J, right? And then again, you just keep all the I's and J's together. And carry out that math. So we get 51.96 in the I plus 590 in the J. And the units on that are miles per hour. Okay. Right, and what they actually asked for is the full ground speed. That would be the magnitude of this. I actually didn't carry out this calc, but it would be the magnitude of this, square root of the sum of the squares of these two components. That would tell me what your overall ground speed is, right? Very little in the I component, right? And then you'd be looking at the course. I think you have a homework problem similar to this. That's what I'm gonna tell you this. I wanna get to the next problem, so. Right, what it's after is this magnitude right here, right? This would be its velocity there. This would be 51.96. Just gotta show you what this in the I, and this would be 590 in the J. So it's all with that little triangle there. And then the course is this angle right here. Is that theta, is how far off of north it is. So when you do the homework problem, that's what it's after, okay? Or it's still slightly different where it tells you the theta and you have to work out some other stuff, but it's all based off of that. Cool. All right. I wanted to get this next one here. We good? Give me a second. Okay, good. Good. I'm gonna go on this one. All right. A little more complicated. I've been talking about this one for a while. You got two cars traveling at a constant speed around circular tracks. Right, one's at A, one's at B. Two different radiuses. Right, RA is 1250, RB is 1200, and they're traveling around these circular tracks. And what it wants us to find, missing a V here. What it wants you to find is the velocity of B is seen from A, and the acceleration of B is seen from A. So if I'm at A and I'm looking back at B, how fast does it appear to be going when I'm doing that? And what does its acceleration appear to be going as I'm going from there? Okay. So then obviously this is a relative motion problem, but then also it is something traveling around a circle, so we're going to do it in polar coordinates, okay? And we're going to use it to figure out what one is doing from the other. We'll go back to our original equation here. Say velocity of B was equal to the velocity of A plus the velocity of B is seen from A, right? And so we could just flip this equation around. Velocity of B is seen from A is just going to be the velocity of B minus the velocity of A. Right? That's the equation we're going to use. Same thing with acceleration. Same argument can be made there. Acceleration of B is seen from A is just going to be the acceleration of B minus the acceleration of A. So we're going to use these two things. So I basically have to get the velocity of B and the velocity of A, the acceleration of B and the acceleration of A. Once I get those, subtract them, and then out pops what we're after. Okay? So we're going to do this per vehicle, and we're going to start out in polar coordinates and do car A first. Car A. Car A, what is it doing? Velocity of A. All right, this is traveling around in a circle. And so this is in a circle because this could be r omega in the e theta direction, or this could be the velocity of A in the e theta direction. Right, depending on if I have omegas or if I have velocities, I can use either one of those. In this case, they tell us what the velocity of A is, and so I'm going to use the one on the right. It's just VA in the e theta direction. So this is going to be 36 in the e theta direction, and that's in feet per second. Okay. In terms of accelerations could be equal to, in a circle, this would be r alpha. It's capital R alpha in the e theta direction minus r omega squared in the ER direction. In this case, these things are traveling at constant velocities. Since it's constant velocities, there is no alpha component, right? This can also be written, this term right here can be written in terms of velocities, right? VA squared over RA. Right, remember how r omega squared and v squared over r? You could use both because of the relationship between velocity and acceleration. We can use either one of those. When we have velocities, we're going to want to use velocities. When we have omegas, we want to use omegas. In this case, we know velocities. Okay? And so this will be negative 36 squared all over 1250 in the ER direction. Okay? So now I know the velocity and acceleration of car A. Then I go down to car B. Car B. What's happening in car B? Same thing. Car B. Velocity of B. Car B is going to be equal to, again, we'll go right to velocity since they tell us. It's going to be VB in the e theta direction. Right, and they tell us that's 45 in the e theta direction, feet per second. So I know what that is. And then I come down to the acceleration of B. again, R alpha is going to go to 0. R alpha in the E theta direction, that's just going to be 0 minus VB squared all over RB. That guy's going to 0. And this is equal to the velocity of B, they told us to be 45 squared all over 1200. 8 per second squared. 8 per second squared. I left my units off there, so there's that. Okay. Right, and this is I've been hinting towards it. So you can carry out the math and figure out what those are. But I need, right, this to do this problem, right? I have to do VB minus VA and AB minus AA. Well, here's VA and then here's VB, right? And you want to just be able to subtract those, right? If I could take this, or sorry, this minus this, and it would tell me what's going on. Why can't I do that right now? They're both in the E theta direction, right? That's in the E theta direction. That's in the E theta direction. Why can't I do it though? I can't do it yet.
They have different radiuses.
No, close. They have different something, right? They have different E thetas, right? Where's the E thetas? Well, this is, I kind of did this on purpose, but if you write where the E theta, right, there's E theta for car A, and ER is this way. Right? And then over here, car B, right, there's my ER, and here's E theta. Right? They're pointed different directions, right? Like, remember this, they're very unique, right? We kept talking about this. It takes a little while to get used to. It's like, well, my E theta for car A is, is this way and then this way, but then over here, my ER or my E theta is this way and my E theta or my ER is that direction. It's constantly changing, and it's totally fine that they're constantly changing. And for most problems, it's totally fine. It's just when you want to compare it to something else, that's when you have to really like buckle down. It's like, okay, well now which direction is ER and E theta actually pointed, right? And so we have to do that little conversion. We have to get them both into the same coordinate system, right? Because, my E theta so this, this guy is actually moving this way, and this one's actually moving that way. And so I have to just get them in the same coordinate system, right? And sometimes people can look at that and then right at the beginning kind of do it on the fly. I like to do it first. I like to do it in polar coordinates first, and then do a conversion into Cartesian coordinates, and then do the subtraction after that, okay? So let's do that. So we got to go over into Cartesian. We got to flip everything into Cartesian. Got to get in the same coordinate system. Okay. Go into Cartesian conversion, right? We say VA is equal to 36 in the E theta direction. Okay. I'm going to cheat, and I'm going to go up and grab the conversion. Where is it at? Right. That's what that was up in our notes up above. Okay. Now, so what I do when I do this conversion, just anywhere I see E theta over here, I just write this instead. Okay, and so that's what we're going to do. VA is equal to 36 times negative sign. In this case, it's going to be 25. Yeah, 25 degrees right here, 25 degrees. Sine of 25 in the I direction plus cosine of 25 in the J direction. Okay, so now that takes my VA and puts it into Cartesian coordinates as opposed to in the other coordinates. So that's it for there. VB, you could do the same thing, right? VB, you could do the same thing, or we could use inspection here, right? You can look at VBs. Right? I'm trying to get this thing into Cartesian coordinates. So which direction is E theta in? It's in the J direction, right? It's pointed straight up there, and ER is going to be straight up in the X direction, right? You could see it. It lines up with it. You could use the same. You could use this same deal. It would just end up being, all the ER would be it directly in the I direction, and E theta would be in the J direction, right? And so by inspection, just to save time, we'll just say that VB is 45 in the J. Okay. We have both of those. And then we do the same thing with accelerations. Acceleration of A is equal to negative 36 squared over 1250. Right, and that's in the ER direction. And then where that ER is at, I just slip in that equation over on the right there. 1250 times cosine 25 in the I plus sine 25 in the J. Using that conversion from above. And then AB is equal to negative 45 over 1200. And that is going to be, all that is in the I direction. Right. Now we could do the addition and subtraction. Right, because now everything's in the right directions. Right, they're in the same coordinate system, rather. They're all in the same coordinate system, and now I could do the subtractions. Right? And so at this point, what you would do, right, you would say VB is seen from A would be equal to VB minus VA, all in Cartesian coordinates. And then you carry out the math. I didn't actually do it. I gave you the very answer at the end, the magnitude. If you want to go back and check this, you can. The magnitude of VB is seen from A. It's just algebra, 19.6 feet per second, if you want to do that problem. And then the same thing, you do the acceleration of B is seen from A. Acceleration of B minus acceleration of A. And then if you carry out that and look at the magnitude afterwards, again, that's the square root of the sum of the squares of these things. And this will end up being 0.87. That's the answer after. Right. I just didn't want to waste time doing the algebra as we go through. But you then, once you, we have it, you do this guy, this guy minus this guy, right? And you'll have i's and j components when you do that. And then after that, you just do the square root of the sum of squares of those i's and j's. And you come down to the accelerations, and you'll do this guy minus this guy. It's going to have i's and j's. You do the square root of the sum of squares, and now pops the answer. I like doing this one just to show you, like, sometimes you do have to use that conversion, right? Because they are acting in different, the ER and E theta, they're in kind of random locations and they're going in different places. Usually we don't care unless you're trying to compare it to something else. When you start comparing it to something else, then you have to go to some coordinate system that's common between the two. All right. We did it, okay? All that is kinematics, right? Our next thing we got to do is kinetics, right? I'm a big fan of kinetics. I didn't. I haven't even got my notes ready yet here. Hold on. Duplicate. So if you printed out another set, or if you already did that, or you have to switch over to a different PDF, we're going to go over to this. Okay, so everything we've done, it's not that, everything we've done so far, right, is all just, they start out saying, here is the acceleration equation, here's the alpha equation, here's what, you start out at that point, and we don't do anything, any force or anything. Now we have to do forces, right? And we're gonna derive what those acceleration equations are. Once we get those acceleration equations, then we solve them how we've just been doing, right? Everything we've done so far, we're gonna keep using, but we're gonna start at a different point and we're gonna derive those acceleration equations, right? I mean, an example of where we're headed, right? I got a block that's hanging from a spring and it starts out at rest and I release it and the thing is gonna fall down and then we're asked to figure out how far down it goes and stuff. So we're gonna go through and we're gonna derive an equation for acceleration. We're gonna look to see what type of acceleration equation it is. Is it a function of time? Is it a function of position? Is it a function of velocity? And then we're gonna solve it using our kinematics, right? Another example would be, here's this guy sitting on a ramp and then we're pulling down on this string. If I pull really hard, the thing's gonna move up. If I pull less, it's gonna slide down. And then we have to figure out how hard we have to pull in order for it to go up or down at a certain acceleration, right? Another example, the car is going over this hill. How fast does it need to go in order to actually jump, right? This guy swinging from a bridge, right? How much tension is going to be in this cord when it swings from a bridge down at the bottom and stuff, right? So that's kind of where we're headed, right? Tied to forces, right? We're going to solve this type of problem with several different methods. Oh, let me get my notes up here. All right. My notes up here, guys. All right. This is where the cool stuff happens. I think it's cooler. All right. Okay. All right. So far, right, what we've been dealing with is just kinematics, the geometry of motion, right? But now we're going to get into kinetics, right? And just to get a little review, I've told you before, we're going to do this 3 different ways. We're going to do FMA, what we call FMA, was force mass acceleration. It was Newton's law. We're going to start out with that. We're also going to do work energy, one of my favorite methods. Beautiful how it works. You may remember doing that from physics. And the last one is going to be impulse momentum. So there's going to be 3 different ways we solve these types of problems. So that's the structure of where we're headed, right? Or I'm going to do F equals ma. We're going to do it in Cartesian coordinates, normal tangent coordinates, then polar coordinates. Okay, we're going to do those 3 things. Then we're going to do work energy, kind of in all of those things. And then we're going to do impulse momentum, which is collisions. And then when we're done with all that, okay, we're going to go on to 2D rigid body stuff. Okay, you guys have an exam next week. Is it next week? Next Friday. Is that correct? Next Friday. So just know that that's coming, right? And what that's going to be on is going to be one problem from kinematics, the stuff we've done up until this point, and then the second part is going to be on an F equals ma problem, which is what we're doing right now. Then the next exam is going to be on work energy and impulse momentum, which is just straight 2 weeks after that. We're going to kind of crank them out pretty quickly. Okay. So 26, is that next Friday?
Not next Friday, the Friday after.
Oh, you got plenty of time. Plenty of time to worry. It's that far out? Look at that. Wow. Maybe we need to slow down. You go too fast. Oh, I know what it is. Do I know what it is? I don't know why that's so delayed. All right. Okay, so the F equals ma. This is Newton's second law, right? This is what I said before. This is FMA. FMA, right? And we're going to use Newton's second law, which says some of the forces, some of the external forces, we'll put the ext, we'll drop that ext pretty quickly. Some of those forces is equal to mass times acceleration in vector. These come from free body diagram. These external forces, right? We got to go back to free body diagrams. This, right? This is our kinematics. Right? We have to do kinematics as we go through these things. Oh, it's 3 coordinate systems, right? So then we're going to do this in 3 coordinate system. Okay. I'm going to do this in 3 different coordinate systems, right? The 3 coordinate systems, same ones we've done before. Cartesian, normal tangent, and polar. Ooh. Okay, so we're gonna start out doing Cartesians, right? So we're just gonna write down that same equation, that vector. Some of the forces, this is really quick derivation. Some of the external forces is equal to mass times acceleration, right? And you just write out, this is some of the forces in the x direction in the I, plus some of the forces in the y direction in the j, plus some of the forces in the z direction in the k is equal to mass times acceleration in the x in the I plus mass of acceleration y in the j plus mass times acceleration z in the k. Right? You just expand these vectors out, and that's what you get, the i's, j's, and the k's components. And the way we actually solve these problems is easiest just to look at all the x's together. Right? I'm gonna look at the x's. Those or the i's, they have to be equal to each other. The j's, they have to be equal to each other. Right? You kind of just separate this into like 3 different problems, basically. Right? Each of those components have to be equal to each other, which leads us to this down here. Okay. So that's what we're going to do. We're going to draw a free body diagram. We're going to look in the x, the y, and the z, right? And then based off of doing this, we're going to get ax, ay, and az, and then we work our way towards like displacements. We go to velocities and displacements, and we do integration when it's required and stuff like that. Okay. So that's where we'll take off. That's what we'll take off on Wednesday. First full week of school, right? Is it say we did a full week last week? I thought we had last Monday off. How many weeks are we into this shit, man? We're in 4 weeks into this? Out of 15, right? Holy shit. We go quick. All right, cool. Man, I've lost it. I lost a week in there. So, all right.
Well, there's like half. So this is really like.
Yeah, cause we half the week. Then we had a full week. Oh, we did. Oh, yeah. Okay.